Hello everyone, and welcome to the period of a simple pendulum post-lab. So there were two variables in this lab that we wanted to test, the mass and the length. Remember that we had shown that the amplitude doesn't seem to affect the period, much as it didn't with our other simple harmonic oscillators. So first part of the lab, right? You looked at the effect of mass on the period, and although I didn't ask you to graph it, if you had graphed it, what would it have looked like? Wouldn't it have looked like this? Yeah, because what effect did mass have? Basically none. I mean, your masses went up by many multiples, right? Many multiples of your smallest to your largest mass from the cork ball all the way up to the lead ball. And so in this case, right, there was virtually no change at all, right? So that means, the way we would write that, is period is independent of the mass. Period is independent of mass. It doesn't affect it at all. Now that's a little interesting, right? Because mass was part of our other simple harmonic oscillators. So we'll have to tease out why the mass ends up canceling out here when we do the proof in just a few minutes. Second part of the lab, a little more complex, but also I suppose in some ways a little more fun as you actually got things to change, was period as a function of length. Period in seconds, length in meters. When you graphed it, you got a side opening parabola. Right? Side opening parabola. To linearize a side opening parabola, well, remember that to linearize a top opening parabola, you have to square the x. So a side opening parabola, we square root the x. So period in seconds versus square root of length in square root of meters gave you a linear graph. Not only linear, but it went through 0, 0, and therefore the period is proportional to the square root of the length. If you double the length, you don't get twice the period, you get the square root of 2 times the period, roughly 1.414. Right? If we pick nicer numbers, if you quadruple the length, you get 2 times the period. If the length is increased by 9 times, you get 3 times the period. Notice how the length goes up faster than the period does. That's why the original graph levels off, right? Slope is rise over run. So the rise goes up slower than the run. You get a graph that levels off. Let's make a math model of our linearized graph. The y variable is, of course, the period. And that equals your slope. Well, I'm going to claim that the theoretical slope is about 2.01 to 3 sig figs. Why 2.01? You'll see when we do the proof in a bit. But I know that this is close to your slopes because otherwise the Google form wouldn't have accepted your slopes. Units, rise, seconds, over run, square rooted meters. That doesn't look like anything we've seen before, so we'll see where that comes from in the proof. The x variable is the square root of the length, and the y-intercept is 0, meaning no length, no period, because it can't swing back and forth. So here is our experimental period of a simple pendulum equation. Okay? Now, it's hard to interpret where this comes from, right, all by itself. But remember, one thing that might be in there, right, is the gravitational field strength. Remember, we said that's kind of the springiness of a pendulum. That's what's causing the pendulum to oscillate. And so that should be a factor in the equation. But since we kept it constant, we can't really tease out how without doing some theoretical proof here. Right, so constant g of course, 9.8 newtons per kilogram near the surface of the Earth. So let's do that proof. Here is a simple pendulum. We consider all of the mass to be in the pendulum bob, which is out at one of its amplitudes. Okay, so it's as far out as it goes on this side. This is the angle that it's at, theta, okay, from the vertical. Remember, the vertical is the equilibrium position, so we would call that angular position 0. Yeah, this is going to be another angular simple harmonic oscillator, right, as it rotates, if you will. Right, moves back and forth. So what forces act on the pendulum bob? Well, obviously, gravity. Oh, sorry, the length of the pendulum bob is L, right? So we're going to call the length L. So the force of gravity, right, acts from the center of gravity of the pendulum bob. So notice here, it's not in the same direction as L, right, as the string, if you will, So couldn't we break up this force of gravity into perpendicular components? One component, which is radial, and one component, which is tangential. Note, this angle is also theta, right? Same angle. Now, why would we choose these? Why would we choose a radial component and a tangential component? Well, remember that radial components exert no torque. So it is only this part of the force of gravity, the tangential component of the force of gravity, which exerts a torque and therefore makes this oscillate. With me there? There's also a force of tension, which is going to act up along the string. Now, here's a little question. How big is the force of tension? Well, first of all, notice that it opposes the radial component of the force of gravity. Are they the same size then? If they were the same size, what would be true? Well, if they were the same size, the net force in this direction, right, would be 0. And this pendulum is going to move in a circle, or at least part of a circle. And don't we also always have to have an inward directed force in order to make something move in a circle? We do. Right? So the force of tension has to be greater than F of GR, than the radial component of the force of gravity. I've seen this pop up on a couple of AP tests, right? Just a little 1 point of a free response problem, right? That you've got to be able to understand why the force of tension has to be bigger than this, right? It's because it's moving in a circle and therefore has to have an inward force directed on it in order to keep it moving in a circle. So, let's talk about the torque that's exerted. Now, first of all, the force of tension and the radial component of the force of gravity exert no torque because they are radial. Right? There's no angle in between. Torque is given by R cross F, or RF sine theta. So the RF sine theta is L, right? That's R. Right? And the force is the force of gravity, right? And theta is the angle in between R and F, which would be theta. Do you notice that F of G sine theta is really F of GT? Right, see that little right triangle right here? Hypotenuse times the sine of the angle is the length of the opposite side. So this is really, if we want to make it the perpendicular kind of thing, right? This is R is L, and this is the part of the force which is perpendicular, right, to R. Okay, so a couple different ways for you to figure out why this is that, right? Now, what about the negative sign? Well, notice, right, theta here is this way. What would that be? Clockwise, right? But F of GT is pointing the other way, right? So they're always opposites one another. But then we have a problem, because we said, right, oh, sorry, F of G is mg, right? But this is a problem because we said that simple harmonic oscillators, even angular simple harmonic oscillators, are supposed to have a torque that is proportional to the opposite of the angular displacement. But this equation says the torque is not proportional to the opposite of the displacement. It's proportional to the opposite of the sine of the angular displacement. That is not a simple harmonic oscillator then. Unless we do one thing. You might have remember that in the lab, I asked you to use small angles. Right? Why? Well, two reasons. One was to save my equipment, right? So you weren't running the pendulums into the photo gate. But the other reason was because of this proof. And we have to do something called the small angle approximation. I never ever heard about this before, but it pops up from time to time in physics. It says that for small angular positions in radians, the sine of theta is essentially theta. Only for small thetas. Now, I'll give you a couple of reasons why. First, I'm going to prove this kind of by example. So let's take a small angle, 9 degrees. That's pi over 20 radians, right? If we take the sine of pi over 20 radians, which is 0.1571 radians, we get 0.1577. That's pretty darn close, right, to pi over 20 if you convert. In fact, that's only off by 0.38%. So if you have an angle of 9 degrees, you're going to get a pretty good result here. It's going to act like the sine of theta is theta. Well, let's look at a bigger one, 30 degrees. Now we're getting to a sizable angle, probably bigger than anything you used in the lab. Well, theta is pi over 6 radians. Pi over 6 is 0.5236. So if you take the sine of that, you get a half, right? Sine of theta of 30 degrees is 0.5. Well, that looks like a little further off, but if you do a percent error calculation, it's only 4.5% error. Now, you start getting into bigger angles, you'll get bigger errors. 45 degrees, which is pi fourths radians, 0.7854 radians. The sine of that is 0.7071. That's the square root of 2 over 2, by the way, right? 1.414, right? Divided by 2. That is 10% error. That's a lot of error for us, right? In physics, we normally have equipment that gets us much smaller error, so probably wouldn't be satisfied with that. But again, I hope you came nowhere near having that big of an amplitude. And if we go even bigger, 60 degrees, pi third radians, now we're going to get 17% error, right? So essentially, if you use a small angle, we can replace the sine of theta with theta in radians. Right? Key there is we got to do radians. Now, why does that work? Well, let's look at a sine function. Right? Look at this part of the sine function. Doesn't that look, at least if you're close to theta here, doesn't that look pretty linear? Right? It does. It comes pretty close to fitting. So if this is our equilibrium position, right? If this y is theta, right? And this is our equilibrium position. If we go a little bit to the left of the equilibrium position, well, it pretty much acts like a linear function. If we go a little bit to the right, it still pretty much acts like a linear function. But notice when you start getting further away, it starts getting further and further off of being linear. So that's why for small angles, sine of theta is essentially theta. Okay? So, if we assume that we're only going to use this simple pendulum for small angles, and we plug that in, now we get a period which is proportional to the opposite of the angular displacement, and therefore will act like a simple harmonic oscillator. It'll act like the torsion pendulum, an angular simple harmonic oscillator. So this is an important thing, okay? An important thing for us to realize that the equation we are about to derive is limited in usage. Depends how much error you want to have. Right? The smaller the angle, the smaller the amplitude, the more accurate this equation is going to actually predict the period. Right? So unlike the other ones that we've looked at, this one's got actually a little extra little thing that you got to remember about it. Okay, kind of how good is the equation. So let's continue on with this. Since this is an angular simple harmonic oscillator, we're going to use the angular version of Newton's second law, which is that net torque is I alpha. And yes, I comes back in. That's an alpha, not an A, right? Well, there's only one torque in this case. It's the torque from the force of gravity, right? And in fact, it's the torque from this part of the force of gravity, as we previously did. So the torque from that part is negative mg L theta, as we derived previously. And we know that for small thetas, it acts like a simple harmonic oscillator, and therefore the angular acceleration is negative omega squared theta, where this is a loaded simple harmonic oscillation theta, right, where theta is theta sub m cosine of omega t plus phi. Right? That theta and this theta, as it oscillates like a simple harmonic oscillator. So it follows the amplitude cosine of omega t plus phi. With me? So we'll plug both of these in, and we get negative mgl theta equals I times negative omega squared theta. Note what happens here. Theta cancels out. Well, if theta cancels out, that means the amplitude cancels out. So here's the physics showing that the amplitude will cancel out. Now again, remember, this is all for small angles, because if you're not using a small angle, this is actually the sine of theta, and the sine of theta is not going to cancel with theta, and you don't have a simple harmonic oscillator. So for small angles, this works. You might not have noticed it, but in my demo, I used pretty small angles. Now, let's talk about rotational inertia. So all of the mass is in the pendulum bob, right? We don't consider the string, or massless rod, if you will, to have any rotational inertia. So therefore, we can treat the pendulum bob as a point mass. And what is the rotational inertia of a point mass? It is mr squared, and r in this case would be L. So the rotational inertia is ml squared. Plug that in, and we get mgl equals ml squared times omega squared. Right? The negatives canceled out too, right? So the negative here and here canceled. And now what do you notice happens? The masses cancel. So, why do the masses cancel? Well, more mass means a greater torque. But more mass, which would tend to make things accelerate faster, right? But more mass also means more inertia, right? And more inertia has a greater resistance to changes in its motion. And those two things cancel. This is our old friend, the equivalence of gravitational and inertial mass, right? Those two different kinds of mass depending on how you measure it. Do you measure it with, F equals ma, or in this case, torque equals I alpha? Or do you measure it, as a part of the rotational inertia? Right? More mass, more torque, more mass, more rotational inertia resisting changes in its angular acceleration. And so they cancel out. Right? So this is why we don't get a mass in this equation, and why you got basically the same value every time you did the mass part of the lab. Note also, one of the L's cancels. So we're left with omega equals the square root of g over L. This is the angular frequency of a simple pendulum, if you remember this one. But I don't want to know the angular frequency of a simple pendulum. I want to know the period of the simple pendulum. So I hope you remember that angular acceleration angular frequency can be written as 2 pi over the period. Right? Angular frequency is 2 pi over the period because it takes 2 pi radians to go through one oscillation, and t is the time for one oscillation. Right? Plug that in. You get 2 pi over the period equals the square root of g over L. Solve for the period. And here is our equation for the period of a simple pendulum, with the provision that it is a small angle, right? Small angle approximation has to be here. So this equation will be more accurate the smaller the amplitude of the oscillation for the pendulum is. Okay? Smaller oscillations better match with this equation. Note that, like all simple harmonic oscillators we've talked about, it has an element of springiness and an element of inertia. Right? The L is the element of inertia because that factors into the rotational inertia of the pendulum bob. Right? So increasing L would increase the rotational inertia, and therefore increase the period. It would take longer to swing back and forth. The G is the springiness part. This is the gravitational field strength. Right? Notice how this pops up in the equation. We couldn't change it in the lab, but it is part of the equation. Note that the larger the gravitational field strength is, right, it's on the bottom of the fraction, the smaller the period will be. It will oscillate faster. Hopefully that makes sense, right, because this would increase the amount of gravity. Right, so that would make it oscillate faster. So note here, the period is actually inversely proportional to the square root of the gravitational field strength. If we manage to do a lab, which we could, but we have to get some very complex equipment. But if we did a lab like that, that's what we would find in the lab. Period inversely proportional to the square root of the gravitational field strength. Now, let's take this theoretical period of a simple pendulum and see how it leads us to what we got in the lab. Right? In the lab, we got something like this with constant gravitational field strength. Well, here's our general math model. So let me rewrite it to look more like our experimental math model. Pull the square root of L out here, leave the square root of G down there, and look. If we have an equation from a graph of period versus square root of L, like the linearized graph of our lab, the slope of this lab must be 2 pi over the square root of G if both of these equations are to accurately describe the period of a simple pendulum. So think about this in terms of an AP test, right? If you graph period versus the square root of the length, you'll get a linear graph, and your slope, right? Your slope will be 2 pi over the square root of the gravitational field strength. Okay? But in this part of the lab, we kept the gravitational field strength constant. This is the slope of a graph of period versus square root of length. So what is 2 pi over the square root of G? Well, that's 2 pi over the square root of 9.8 newtons per kilogram. Let's check out the units. 1 over the square root of a newton per kilogram does not look like a second per square rooted meter until you remember that a newton is a derived unit and is in fact a kilogram meter per second squared. Now the kilograms cancel. The second squared pops up to the top, but it doesn't stay a second squared because it's square rooted. Square root of a second squared is a second, and therefore we end up with seconds per square rooted meter, exactly as we did in the lab. And I bet you can't guess what 2 pi over the square root of 9.8 is. Yeah, it's 2.01, right? Knowing the equation, right, this is what I therefore predicted your slope should be. And in fact, right, it is. Let's look at some data. Here's some data from a couple of years. You look this up, you'll see data from 2019 and 2021. Right? We took a break over this unit in 2020. And here are the slopes that people found. You'll notice they are all very close to one another. I mean, very, very close to one another. We're talking hundredths, right, here. And they average out to 2.01. Our theoretical slope, if we take 2 pi over the square root of G, is 2.007 if I take it out even one sig fig further. And of course, that averages out to 2.01, which means we have 0% error. But look at the sizes of these errors. They're tiny, right? They're tiny, 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 tiny percent errors for what we do. So this equation is a really good match to reality if, and only if, you use smaller angles, right? The smaller the angles, the better the match. So keep that in mind, please. Right? But it actually wasn't a hard lab to match, right? It wasn't a hard lab to do. The PhotoGate did much of the heavy lifting of measuring the periods correctly. You pretty much, any error you have is going to mostly be from using incorrect lengths, right? Not getting the lengths exact, since that's really the only factor that affects it other than the gravitational field strength, which we weren't changing. Right? It's all about getting the right length in there. But you seem to do a pretty good job, at least on average. So here is our equation then for the period of a simple pendulum.